Hi everyone. I'm going to review the remainder of the material for the biopsychology unit. So I know we've already talked some about the neuron, but we did not finish that material. So I'm going to start with the neuron, and then we'll talk about the nervous system and finally the endocrine system. So for the nervous system, we talked about how we have two basic cell types, the glial cells and the neurons. The glial cells we used to call nature's packing peanuts, but they actually really support the neurons in important ways. The neurons, though, are our communication system in our brain, so we'll spend a lot more time on neurons. So we've got the picture of the neuron here that you can review, as well as the graphic that I really like to help me remember, which is the arm. So we've got the cell body here in the palm, the dendrites are reaching out, and then the axon's the long spindly piece. If I had some beautiful bracelets, I could make a myelin sheath, big chunky myelin sheath. And that's a fatty substance that helps the messages to move faster. So we were able to try out this exercise in class with the candy, but neurons, we're talking about communication first between, how it happens in one neuron, and then how it happens between neurons, so multiple neurons. So within one neuron, we've got the neuron's membrane is at a resting potential. If something happens, some signal is received, then we see the sodium and the potassium kind of moving in and out of the cell, which causes us to have this action potential. So the sodium is initially outside the cell, it moves in, potassium's inside, it moves out, and so we can kind of see this process occurring all along the length of the axon. This process, when it occurs, we call it an action potential. So for an action potential to occur, we have to have the neuron receive a signal. It needs to be up enough to excite the neuron up through the threshold of excitation. So action potentials are all or none. So they either happen or they don't. There's no partial action potential. So one of the good examples provided in class is getting pushed off a cliff. So you're either pushed off the cliff or you're not. There's no halfway off kind of thing, like you're falling in the abyss or you're up on dry land. So we kind of see that's the same thing with the action potential. There's also videos linked in that you can review from YouTube. Crash Course makes a good series of videos on neuron communication as well as the nervous and endocrine systems. So Crash Course is always a good place to go for videos. But communication at the synapse, this is communication between neurons. So the synapse is really just this tiny, tiny, tiny space, so much slimmer than even one human hair, space between two neurons. And here we see each of these neurons will have receptors, and so then we have neurotransmitters, which we talked about. Dopamine was the one we talked about the most, but neurotransmitters such as dopamine fit into certain receptors, so this lock and key relationship. So the dopamine will be the lock, and it's going to fit into the key of a certain neuro receptor. So neurotransmitters, what these actually are, we'll talk about some examples of them, but where we see them released is when the action potential, so it's moved all the way down, we've got the information coming in and moving all the way down through the axon. Once it gets to the end of the axon, to the terminal buttons are where this neurotransmitter is actually released into the synapse. So the synaptic vesicles are what's going to release those neurotransmitters, and those neurotransmitters are then going to bind to the receptors on the adjacent neuron. So they're going to be in that synapse, and they're going to be kind of pulled into this next neuron, which will start the action potential, or hopefully will start the action potential in the neuron that's just received those neurotransmitters. So then this should be communication between the neurons, with one neuron receiving information from its dendrites, having that action potential start all the way down the axon, releasing neurotransmitters through the synaptic vesicles, releasing their neurotransmitters into the next neuron, and then the next neuron would have that same process occur with the action potential and would release to the following neuron. And this process happens extremely quickly and is very accurate. So that was kind of unlike our, trying to get a message down our line of students that we tried in class, where we had to kind of repeat the same message. This is, always pretty highly accurate and very quick. So neurotransmitter function, most of what we know about how neurotransmitters work is from studying drugs, from psych disorders. We know that some neurotransmitters are agonists, or that we have some that we call agonists. So these mimic neurotransmitters at the receptor site. Some are antagonists. These will block the activity of a neurotransmitter. And these are actually the drugs. So not the necessarily the neurotransmitters themselves, but these drugs that we would prescribe for psychological disorders. Some will mimic the neurotransmitter. Others will block the activity of a neurotransmitter. So this isn't only prescription drugs. It's also recreational drugs that can have this effect. These are some of our major neurotransmitters, though. So we've got acetylcholine. You can kind of read through. Dopamine is one we've talked about. Serotonin is one we'll keep coming back to in the course, as it's really relevant to depression. I love this comic. So serotonin and dopamine, technically the only two things we enjoy. Many of these pleasurable activities are releasing the serotonin and the dopamine. So it's, kind of yeah, reuptake inhibitors. So we've talked about serotonin being important for psychology, and that we're going to keep coming back to serotonin as we go through the course. One reason why is because of depression, which we know is very, very common. And one major medication that we provide is this at the bottom, selective serotonin reuptake inhibitors, SSRIs. So what these do, when we have reuptake, we've got the two neurons who are very, very close together. They've got synapse between them. The presynaptic neuron has released these neurotransmitters, and they're in the synapse. The postsynaptic neuron is, bringing them in like a lock in the key. So they're bringing in and reading kind of those neurotransmitters to have an action occur. Well, reuptake is what happens with the presynaptic neuron. It will take back what it's already kind of, take back those neurotransmitters that it released into the synapse. And so what we can provide patients then is a reuptake inhibitor. So it will stop that process, so that first neuron can no longer bring all of its neurotransmitters back. Instead, those neurotransmitters just kind of hang out in that synapse, and they're longer, which allows the postsynaptic neuron to pull them in. So the neurotransmitters effectively stay there in the synapse and increase their effects. So that's what we have for serotonin with SSRIs. This medication is really common for depression. They just leave, we've got that beautiful graphic there, they just leave the serotonin in the synapse for longer. And that will bring us into the nervous system. In our nervous system, we have two major subdivisions. So we'll talk about the central nervous system mostly, so we're going to talk about the brain quite a bit. Also the peripheral nervous system we'll talk about as it relates to stress and health. The peripheral nervous system, we've got bundles of axons, so we call these nerves, and they're going to help us carry messages between the central nervous system and the muscles, organs, and senses. And so one of the main areas of the peripheral nervous system that we'll talk about is this autonomic nervous system, the ANS. So the ANS is going to be divided into the sympathetic and parasympathetic divisions. So we've kind of got a lot of division there. We've got from, this nervous system having a central nervous system, peripheral, so we're in the peripheral, and then from this somatic and autonomic, we're in the autonomic, and then the autonomic itself then is sympathetic and parasympathetic, has this division there. So the parasympathetic is something that helps us, we kind of call this a rest and digest. It helps to kind of bring us into this this situation where we can kind of be calm, nothing's really going on that's too excitable. The sympathetic nervous system, in contrast, kind of turns on when we need the fight or flight response, some kind of activity needs to happen. So these will work together. The body really wants to be in homeostasis, so we want to have, not be too focused on either one of these. We want them to kind of be in balance. So if our sympathetic nervous system has turned on, we're preparing the body for stress, for fight or flight. After that, stressor has gone away, then the parasympathetic nervous system will help return the body back to normal. We'll watch a video of this in the stress unit called Stress Portrait of a Killer, but it really shows this, the sympathetic nervous system and how we're activating it for so many stressors that are really psychological in nature, stressors that are even in our head. So in our past, we would activate our sympathetic nervous system if a lion was chasing us, or if we saw a tornado coming and we were in the open fields. That's when we would activate our sympathetic nervous system. But for many of us now, we activate it in traffic, or if we think about our mortgage or our student loans, things that are psychological in nature that we're thinking about that may or may not be present, but our body doesn't really know the difference between those things. And so we're still activating then that sympathetic nervous system, feeling that stress all the time, and then that's what actually leads to health issues with stress. The brain and spinal cord, we won't spend a lot of time on the spinal cord, but we've talked about how this has its own system of automatic processes in class. So those are reflexes. So if you touch a hot pan, you don't have to sit and kind of think and have that message go all the way up through your brain where you kind of decide, should I move my hand or should I not? You don't have to go through that process. We just go, whoa, and get our hand out of there. So it's a reflex. Brain is where we're going to spend a bunch more time, so the brain is really exciting. The brain. So we've got a picture of a brain there, like a real brain, and then some animated brains. But we'll talk about the left and the right hemisphere. So sometimes people make a really big distinction between the left and the right brain, and they think they're these totally different things, but actually we don't really see that. From a scientific perspective, there is some lateralization in each hemisphere, which means that there is some areas that we know are really more focused in language or in other processes. So the left hemisphere is often implicated in language. But the left half of the left hemisphere, it controls the right half of the body. The right hemisphere controls the left half. So, if you have a stroke here in the right side of your body, we would expect, or my right, we would expect the deficits to show up in my left side of my body. So we call that contralateral control. The two hemispheres of the brain are connected by the corpus callosum, which is a really thick band of fiber, and then we've talked about the lateralization. So a lot of what we know about the brain is from studying people who have experienced brain damage. So we've got a couple extreme cases we'll talk about, but then other things like strokes. If someone has a stroke and we suddenly realize that they're having difficulty with understanding speech, then we know wherever that damage was in the brain has to have something to do with speech, or at least it's very likely. In some cases of severe epilepsy, too, we've done a split brain surgery. So I haven't done one. I say we, but I haven't. Psychologists have. So they actually go in here and separate those two hemispheres. They cut through that corpus callosum. And that way, if a seizure activity starts in one hemisphere, it can't easily be transmitted to the other hemisphere. So it kind of stops that communication, but it also gives us a lot of really interesting deficits. So we get to the parts of the brain. So for this one, we're just kind of looking at forebrain, midbrain, and hindbrain. So we're going to split and talk a lot more about the forebrain than we do the mid or the hindbrain. But the forebrain has our cerebral cortex, which we'll talk about quite a bit, as well as some of these subcortical structures. So especially the limbic system, we'll talk about those functions. So we'll split the four lobes of the brain up. So this, from the previous slide, we're going to be talking about this outer surface of the forebrain. And what we see here is if you take that, you can kind of split this information into different lobes. And each lobe is going to have functions that are associated with it. Our frontal lobe is not fully developed until we're around age 25, but it controls a lot of the planning, coordinating, choosing whether or not to do something, inhibitions, higher level cognitive functioning. Also contains Broca's area, which is really important for language. Phineas Gage is one of those extreme examples. We've talked about him a little bit in class, but they've got him posed there with the iron rod that went through his head. So he was a railroad worker, and he was laying these iron rods, and one actually did go up through his head in this depiction. Kind of shows where that went through. And what they were surprised about with Phineas Gage is, long he lived. That's pretty surprising. But then also that he had a lot of personality changes. So he went from being kind of a calm man to more of a more aggressive person, didn't really have good impulse control. And so that kind of told us that if you, damage this frontal lobe, that we're likely to see a loss of some of these important functions for self-control. The parietal lobe, I love this homunculus here, this little thing that looks kind of like a small monkey with giant hands. I really don't know how to describe it, but the parietal lobe, when we look at this, what it does generally is help us process information from the brain, the body's senses, so touch, temperature, and pain. But what that little monkey-looking guy is showing us is what we would look like if our senses were represented as they are in our brain. So what it's trying to show us is that the areas of the lips, the hands, those especially the tongue, the ears, that we get a lot of sensitivity from those areas. So if you were to touch your hands, you're going to feel very, very small touches compared to touching the backs of your legs or this part of your arm here. So we've got a lot more sensitivity and a lot more brain area that corresponds to sensitivity in those certain areas. So if our brain was actually, all that sensitivity in our brain was actually represented in a human physical form, we would all look like this dude. The temporal lobe, this helps really with auditory information. So we see Broca's area in there as well as Wernicke's area. Broca's area, if you have damage there, it's hard for you to produce language. In Wernicke's, it's hard for you to understand language. And there's some videos on the internet you could Google for both of these if you were interested to see more about that. The occipital lobe, this is where we've got the primary visual cortex, so it's helping us to understand what we see. So this brings us to those subcortical structures. The thalamus is a sensory relay, so we get a lot of sensory information through the thalamus. The limbic system is something really, really important. So with the limbic system, the hypothalamus helps us with our processes like sleep and sex, helps keep the body in homeostasis. The amygdala is really important for emotion, so especially like fear and anger. And then the hippocampus is something we learned a lot about through one of our other exceptional cases, which we'll talk about in a second. But the hippocampus is really central for forming new memories. So for learning and forming memories, the hippocampus is really, really needed. And we saw this through the case of HM. So HM was a young man who had seizures, and he underwent surgery for these seizures, and during the surgery, his hippocampi were removed. And so after he had lost that brain region, his seizures got much better, but he couldn't make any new memories. And he also forgot about a decade of his life prior to the surgery. So he just couldn't remember anything like new people, new cities, anything like that he had been in. The tests he took, he thought they were all brand new, even if he just took them. He just couldn't remember anything. But they found that he did get better at some of the things that they asked him to do. So they asked him to fill out a maze. He would get better at that maze, but he didn't remember doing it before. So he was learning in some way, but had no memory at all of learning those things. The midbrain, we won't spend a lot of time on the midbrain, but the reticular formation, as well as the VTA, these are important parts of the midbrain. The hindbrain, we've got the medulla, the pons, the cerebellum. So these are important for life-sustaining functions. The cerebellum helps us control balance. So if you see the test that police officers will ask individuals who may appear intoxicated to do, where they have to put their arms out and walk that straight line. They're kind of testing if cerebellum has been affected by alcohol, because if it has, you can't really balance. So, so to actually get in there and see the brain, we've got some brain imaging techniques. Some of these involve radiation, so obviously, we have to be mindful of that. So CT scans as well as PET scans. These are things that we use radiation for, but then we can go in there and see the PET scans. I think are pretty fascinating because you can see the blood flow. But because they do involve radiation, we've kind of relied more heavily now on techniques with magnetic fields, like the fMRI, the functional MRI. So what this does is tracks both blood flow and oxygen in the brain. We also use the EEG, so those use electrical activity. Those are especially used in things like sleep studies. It's the cap where you see all the electrodes affixed to the scalp. So those are some of the main ways we get images of brains. Hi, that leads us to the endocrine system. For the endocrine system, the most important things really to understand for the purposes of this class is that hormones are released through this endocrine system, that these hormones are really, they're widespread effects. They go through the bloodstream. They help us to regulate bodily functions. And where they're important for psychology is kind of understanding these major glands. So the pituitary gland we'll get back to in lifespan development when we talk about that. It helps control many of the functions. They call it a master gland. The thyroid gland, I think we talk a little bit about that one in motivation and emotion with hunger, but it helps us to regulate a lot of our appetite. The adrenal glands will come back up when we talk about stress and coping. So with this, we've got the adrenal glands releasing, these cortisols and things like that that help us to regulate our stress response. The pancreas is important for blood sugar, and the gonads. So the gonads, we'll talk about that in motivation and emotion, talk about human sexuality. Our gonads are what kind of release those hormones to help us regulate that. So that will finish us up with biopsychology, and I will talk to you all later. Have a good night.